Have you ever wondered what it would feel like to cut across the sky faster than the Earth spins beneath you? That moment when the world below turns into a blur and the horizon bends to your will. For decades, that dream belonged to just a few lucky passengers, those who once stepped aboard the Concorde. It was speed, it was style, and it was the closest most of us ever came to touching the future. And then, it was gone. But here we are again, on the edge of a new chapter. A chapter where the Boom Overture promises to bring supersonic travel back. Not as a distant fantasy, but as a flight you could actually book. The difference? This time, it's being built with technology that simply didn't exist in the Concorde era. And at the heart of it all is its wing. Now, if you stick with me until the very end of this video, you're going to discover exactly why this wing isn't just a piece of metal shaped for lift. It's a piece of art, one that engineers believe will change the way the sky feels beneath an airplane's body. By the end, you'll know the hidden aerodynamic choices that give the Boom Overture its edge, and you'll be able to see why aviation experts call it the wing built for the future. But before we dive into the engineering, let's talk about why the wing even matters. If you've spent hours looking up at the sky or sitting by an airport fence, you already know. Airplanes are not just machines, they are stories in motion. Every curve, every surface, every rivet has a purpose. For airplane lovers, the wing is more than a lifting surface. It's the soul of the aircraft. And here's where psychology comes in. Humans are wired to notice beauty in function. Think about it. The arched back of a cheetah mid-sprint, the perfect curve of a racing yacht's sail, the tapered blade of a samurai sword. Our brains respond to shapes that tell a story of purpose and performance. Airplane wings, when designed right, trigger that same fascination. They make us lean forward in our seats, eyes following the sweep, imagining the airflow rushing over them at hundreds of miles per hour. Boom Supersonic knows this. That's why their Overture isn't just another airliner with a slightly better fuel burn. They have framed the wing design not as a compromise between speed and safety, but as a celebration of both. This is something that has not been done in passenger supersonic flight since the 1970s. Let's rewind for a second. When Concorde was designed in the 1960s, engineers had a simple mission: go faster than sound. They did it brilliantly, a marvel of its time. But the shape of its delta wing, while perfect for piercing the sound barrier, came with compromises: enormous fuel consumption, high landing speeds, and limited efficiency when flying subsonic. It was a one-trick masterpiece, and that trick was expensive. The Overture's wing takes a different psychological and engineering path. Its form says, I'm built to go fast, but I'm also built to endure. It's a gull wing design, an upward curve, almost organic in the way it rises from the fuselage before sweeping back. This subtle curve is not just for aesthetics. It is an aerodynamic strategy to reduce drag and increase lift efficiency across different speeds, including subsonic cruise. Why does this matter? Because this means it can be as graceful at takeoff and landing as it is at Mach 1.7. And here's something else airplane lovers appreciate. The wing isn't isolated from the rest of the body. In the Overture, the integration is seamless. You can trace the airflow with your eyes. You can almost see how the air will hug the surface, break over the leading edge, and smooth out along the fuselage. This kind of harmony between wing and body is rare. It's the same principle behind high-performance fighter jets, but tuned for commercial comfort. Psychologists say that humans are drawn to objects that suggest both power and control. We like seeing a sword that's sharp but perfectly balanced in the hand. We love a sports car that's fast but hugs the road with precision. The Overture's wing design triggers that same dual admiration. It promises speed, but also mastery over that speed. And for those of us who have spent our lives loving aircraft, that's irresistible. Imagine 2026. You're standing on the tarmac, watching this aircraft taxi into position. The wings catch the light differently from anything else around. You know, just by looking, that these aren't the wings of a conventional jet. They are the wings of a machine that will cross oceans in half the time while sipping less fuel than the Concorde ever could. And in that moment, you realize, this is not nostalgia, it's progress.
So why should you keep watching?
Because in just a moment, we'll peel back the layers, literally, to see the science behind how this wing works. We'll talk about the aerodynamic secrets buried in its shape, the NASA-backed research that guided its curves, and why its performance will feel different not just to the engineers, but to every passenger on board. If you've ever felt the rush of takeoff, or the subtle lift as an aircraft banks through the clouds, then what comes next will hit you right in the heart. When you see the Boom Overture in profile, the first thing you notice is how the wings seem to rise and sweep back with purpose. It's not just a visual choice. Every angle, every curve is dictated by the invisible hand of aerodynamics. the science of moving through air with the least resistance and the greatest control. Air moves differently when an aircraft passes from subsonic to supersonic speeds. Below the speed of sound, the goal is smooth, laminar airflow, air that glides over the surface with minimal turbulence. Above the speed of sound, something extraordinary happens. Shock waves form, and the aircraft begins to ride on a cushion of compressed air. If the wing is not shaped perfectly, those shock waves can create enormous drag, slow the plane, and waste fuel. This is where the Overture's gull-wing design becomes more than a beautiful silhouette. Its upward curve allows the wing root, the part where it meets the fuselage, to sit higher than the tip. That geometry changes how the air meets the aircraft, reducing interference drag between the wing and fuselage. It's a subtle gain, but at supersonic speeds, small gains translate into huge performance benefits. The sweep of the wing, that backward angle, is equally critical. A swept wing delays the onset of shockwaves by effectively lowering the speed of the airflow over the wing relative to the aircraft's speed. In other words, the plane can fly faster before shockwaves become a problem. This is not guesswork. It's the result of decades of research, from early NASA wind tunnel experiments in the 1950s to advanced computational fluid dynamics simulations today. For supersonic efficiency, engineers often choose delta wings, large, triangular surfaces like Concorde had. But delta wings, while great for high-speed cruise, are inefficient at lower speeds, making takeoffs and landings tricky. They require higher approach speeds, longer runways, and burn more fuel at subsonic cruise. The Overture's gull wing with a moderate sweep is a hybrid solution, taking the stability and speed of swept wings while improving lift at lower speeds. This is one reason why Overture is expected to use 20% less fuel than a Concorde for the same mission profile. Another critical factor is the aspect ratio, the ratio of a wing's length to its width. The Overture's wing has a higher aspect ratio than the Concorde's, meaning it is longer and narrower relative to its chord. This improves aerodynamic efficiency by reducing induced drag, especially in subsonic cruise. It's the same principle behind glider wings, adapted here for a supersonic aircraft. Beneath the smooth carbon composite skin lies the real engineering magic. Carbon composites allow for precise shaping. Engineers can design the exact curvature they want without being constrained by the limitations of metal. In metal wings, changes in temperature, especially at supersonic speeds where skin temperatures can exceed 120 degrees Celsius, cause expansion and structural stress. Carbon composites resist heat and maintain their shape, meaning the wing's aerodynamic profile stays optimal throughout the flight. The leading edge of the wing, the first part to meet the oncoming air, is carefully designed to manage shock waves. Its angle is sharper than that of subsonic aircraft, but not as extreme as a fighter jet's. This balance keeps drag low, without making the wing overly specialized for high speeds. At Mach 1.7, the Overture's intended cruise speed, the shape allows shockwaves to form in predictable locations away from critical control surfaces. And speaking of control, the placement of flaps and ailerons on the Overture's wing is another quiet revolution. On many supersonic aircraft, control surfaces had to be small or moved to the tail to avoid disruption from shockwaves. But thanks to the Overture's tailored wing sweep and thickness distribution, engineers can place larger, more effective control surfaces along the trailing edge. That means smoother handling, gentler banking, and better passenger comfort, even at speeds that would rattle older designs. The science behind this wing isn't just about making the aircraft faster, it's about efficiency. In aerodynamics, efficiency is a kind of hidden currency. It's what allows you to go farther with less fuel or faster without more thrust. Every contour of the Overture's wing was shaped to make sure no drop of that currency is wasted. Even the underside of the wing has been given attention. At supersonic speeds, the airflow below the wing must be managed just as carefully as the flow above. A miscalculated curve could lead to instability or buffeting, the kind of vibration that wears out both machine and passenger patience. The Overture's designers have smoothed the underside to guide the air cleanly back to the tail, keeping the aircraft steady even during sudden maneuvers. Psychologically, this kind of precision matters to the audience who loves airplanes. It's not just that the wing works, it's that it works because someone understood the invisible patterns of air and found a way to dance with them. It taps into our fascination with mastery over nature's raw forces. When you look at the Overture's wing and know the thought that went into every millimeter, you don't just see an aircraft. You see a conversation between human intelligence and the laws of physics. And there's something even deeper. The knowledge that all these choices, from sweep angle to composite layering, are made for real-world skies, not just computer models. The Overture will have to face turbulence, crosswinds, and the unpredictable moods of weather, all while maintaining the elegance and control promised on paper. The science behind the wing is what makes that possible. It's easy to think of wings as static parts of a plane, but at supersonic speeds they are alive with forces shifting every second. Lift, drag, pressure, temperature, all changing with altitude and velocity. The Overture's wing is built to adapt, to hold its shape and performance across a range of speeds that would challenge most airliners. And that adaptability is why so many in the aviation world are calling it a leap forward. Designing an aircraft for supersonic speed is one challenge. Designing it for the skies of 2026, with today's environmental rules, material science, and passenger expectations, is another entirely. The Boom Overture's wing does not exist in isolation. It is the product of a larger vision, one where speed, sustainability, and safety are all given equal weight. At its core, the Overture's engineering is built around one truth: the world will not accept a supersonic jet that ignores fuel efficiency or noise. Regulations are stricter. Airports demand quieter takeoffs and landings. Communities under flight paths have greater influence than ever before. This means the wing design must work hand in hand with the engines, fuselage, and even the flight path planning. Carbon composite construction is central to meeting these demands. Unlike the aluminum skins of the Concorde era, carbon composites allow for precise shaping and smooth surfaces that maintain aerodynamic integrity over time. These materials are also lighter, a critical factor when aiming to balance high speed with fuel economy. Every kilogram saved in structure can be reallocated to fuel range or passenger amenities. But there is another advantage of composites: resilience. At Mach 1.7, the outer skin of the wing will face aerodynamic heating that can push temperatures above 120 degrees Celsius. In metals, repeated heating and cooling cycles can cause expansion, contraction, and micro-fatigue over years of service. Carbon composites resist these thermal stresses, ensuring the wing's shape and performance remain consistent for decades. The structural design is equally forward-thinking. Internal spars and ribs are laid out not just for strength, but for maintaining exact aerodynamic profiles under load. At high speeds, lift forces bend wings upward. If the wing flexes too much, its shape changes and efficiency drops. Overture's engineers have optimized the internal layout to limit unwanted deformation while still allowing enough flexibility to absorb turbulence without transferring harsh motions to the fuselage. Noise is another critical challenge. Supersonic aircraft are often associated with thunderous takeoffs and the infamous sonic boom. While the sonic boom itself is addressed more by flight altitude and route planning, the wing plays a role in noise at the runway. Its shape and integration with the engines help manage airflow to reduce vortex shedding and wingtip noise during low-speed operations. This, combined with modern engine nacelle designs, means Overture can approach the noise footprint of today's subsonic airliners. Efficiency at subsonic speeds has also been engineered into the wing from the start. Unlike Concorde, which was optimized almost entirely for cruise at Mach 2, Overture is expected to spend portions of its flight below the speed of sound, especially over land. The wing's higher aspect ratio and refined sweep angle allow it to maintain good lift-to-drag performance at these slower speeds, saving fuel and reducing operating costs. Integration with the fuselage is another key to its success. The smooth transition from wing root into the body reduces interference drag, the turbulence created when airflow meets two intersecting surfaces. This is more than an aerodynamic tweak. It also improves structural efficiency, distributing loads more evenly across the fuselage and wing joint, which is one of the most highly stressed parts of any aircraft. In the cockpit, pilots will experience these engineering choices in a way that's invisible to passengers. The wing's stability across varying speeds means fewer constant adjustments, making high-speed cruise feel almost routine. For pilots trained on modern fly-by-wire systems, this predictable behavior is essential. It allows the aircraft to respond smoothly to control inputs, even when crossing from subsonic into transonic and then into supersonic flight regimes. Passenger comfort, while not a direct function of the wing, benefits enormously from these design choices. Reduced drag means less engine thrust is needed, which lowers cabin noise. Better lift characteristics at lower speeds mean smoother approaches and gentler climb rates. Even the way the wing deflects turbulence is tuned to avoid sudden jolts, giving passengers the sensation of gliding rather than being pushed through the air. Looking ahead to 2026, this wing has been designed not just for today's rules, but for the regulations of the next decades. Environmental pressure is only going to increase. The International Civil Aviation Organization and various national agencies are already signaling stricter emissions caps. By building efficiency into the wing from the beginning, Boom is preparing the Overture for compliance well beyond its entry into service. It's also worth noting that the Overture's wing has been designed for adaptability. The aerospace industry evolves quickly. Engine technology, materials science, and computational modeling are advancing year by year. A wing that is too rigid in design could be obsolete in a decade. Overture's engineers have left room for incremental improvements, whether that means refined leading-edge shapes, new control surface designs, or next-generation composite layers. There's a certain poetic symmetry to this. In the 1960s, engineers chased speed above all else, and the result was a marvel that could not survive changing economics and public expectations. In 2026, engineers are chasing balance, speed, efficiency, and sustainability combined. The Overture's wing embodies that balance, proving that engineering is not just about solving technical problems, but about anticipating the world those solutions will fly in. And for airplane lovers, there's something deeply satisfying about this approach. It is a reminder that the future of aviation is not just faster, it is smarter, cleaner, and more enduring. The Overture's wing is not being built for a single era of aviation. It's being built to carry the dream of supersonic flight into a new age, one that could last far longer than the brief, dazzling career of its famous predecessor. Every piece of engineering has a reason, but the ones that endure also have a soul. The Boom Overture's wing is not just a product of equations and simulations. It carries an emotional weight, a reminder that human beings have always looked at the horizon and wondered how to reach it faster. For airplane lovers, wings are more than mechanical structures. They are the purest expression of flight. When you look at the Overture's gull-wing curve, it stirs something deep. The same way a musician feels a connection to the shape of a violin or a sailor feels to the sail of a ship. It's the intersection of form and function, where beauty is born from necessity. Psychologists talk about the law of simplicity, the idea that the human brain prefers designs that appear effortless, even when they are incredibly complex underneath. That's exactly what this wing offers. To the untrained eye, it might seem like a graceful sweep of material. But to those who know aviation, every line tells a story. The calculated sweep angle, the precise dihedral rise, the subtle taper toward the tips. It's a visual poem written in the language of lift and drag. There's also something about curvature that humans instinctively respond to. Sharp, angular shapes can signal danger, while smooth, flowing lines suggest safety and control. The Overture's wing doesn't just look fast, it looks balanced. It reassures the viewer that this speed is not wild and uncontrolled, but harnessed, like a thoroughbred guided by an experienced rider. This feeling matters more than most people realize. The history of aviation is filled with designs that were technically brilliant but failed to inspire the public's imagination. Airplanes, especially those promising something as ambitious as supersonic travel, need more than performance stats. They need to spark an emotional connection strong enough to make people believe in them before they ever step aboard. And that belief is contagious. From a psychological perspective, anticipation is one of the most powerful emotional states. Studies show that the human brain releases dopamine not just when we experience something, but when we anticipate experiencing it. This means that the sight of the Overture's wing, its distinctive silhouette at an airport or in a promotional photo, can trigger excitement long before the engines ever spool up. For those who remember the Concorde, the Overture's wing may also stir nostalgia. Not because it looks the same, it doesn't, but because it represents the return of a lost chapter in aviation. The shape tells you that this aircraft will move differently, cut through the air in a way that subsonic planes never could. It whispers of shorter flights, new possibilities, and the thrill of pushing past old limits.